Okay, so let's look at the availability heuristic. This is the idea that events are more easily remembered, or events that are more easily remembered are judged as being more probable than events that are less easily remembered. So, a good example of this is people's fear of flying. So, many people refuse to fly. Many people express a fear of flying. They think that some disaster is going to befall them as they fly. The plane is going to crash. Something crazy is going to happen. Even though these same people are not nervous to get in their car and drive to the airport, even though statistically the drive to the airport is much more dangerous than the flight itself. This is probably due to the availability heuristic, right? People are making this judgment about risk that doesn't seem to make any sense. The car ride is much more dangerous than the flight, but they're afraid of the flight. Probably because anytime there's a flight disaster, a plane crash, or things like 9/11, they get tons and tons of press, right? They're highly emotional. People hear about them all over the world. They're in the news for days or weeks or even months. And so they're highly available. It's easy to think about them because you hear about them so much, even though they are much less likely to occur than uh, a something more common like death from a car crash. So, of course, we have some data on this. Uh, Here we see some summary data from an experiment that asked people to compare two causes of death and pick the cause of death that is more likely. So, we'll take this first one as an example. Which is more likely, that you will die of homicide or that you will die of appendicitis? And here, homicide is actually 20 times more likely than appendicitis. So the correct answer is homicide. And we see that only 9% of people got it wrong. So this is the percentage of people who are incorrect, who pick the less likely outcome. So when given this comparison, 9% of people picked appendicitis. That's pretty good. 91% of people correctly identified homicide as more likely than appendicitis. But we get some weird results when we start to get into things that maybe are less common, or that we hear about less than homicide. So when we compare drowning to auto train collisions, so a car being hit by a train, drowning is 5 times more common than death by a train collision. Yet we get this big jump. 34% of people get it wrong. 34% of people choose the auto train collision. Probably because when a car gets hit by a train and someone dies, that makes the news, right? That's a huge story. In fact, I mean, that could be like a story across the nation, right? Whereas if someone drowns in their bathtub or in their backyard pool, it's not likely to make the news. So even though most people are correct, we get a lot more people who are incorrect about this. My favorite examples are the last two. When asked to compare asthma to tornadoes, in reality, asthma is 20 times more likely to kill you than a tornado, but 58% of people choose tornado. Why? Because tornadoes are big, they're scary, they're emotional, they make headlines, they make the news, you hear about them. Whereas when someone dies of asthma, you don't hear about it on the news, even though it's 20 times more likely than death by a tornado. And then people really got this last one wrong. Twice as many people die from appendicitis than from pregnancy. But 83% of people think that pregnancy is more common for death. So people are using the sort of the heuristic, the rule of thumb, that if I hear about it more often or if I see it more often, it's probably more common. And that's just not true. Just because you hear about something or see something a lot does not make it common. Our next heuristic is illusory correlation. This is basically you think that a relationship exists between two things, even though it doesn't, or is much weaker than you think it is. So, a good example of this are things like superstition. So, every time I wear my lucky socks, my football team wins. In reality, your disgusting lucky socks have nothing to do with your football team winning. But because of your faulty thinking, you remember, and this might actually involve a little bit of the availability heuristic too. You remember all the times that you're lucky, that when you wore your lucky socks, your team won. And so then you draw an illusory correlation, right? That there's a relationship between my lucky socks and my football team, even though there's not. Lots of baseball players actually refuse to step on the foul lines as they come on and off the field, thinking that it's bad luck to step on the line, so they jump over it. These are sort of silly examples, but they illustrate the larger point that people very easily connect two things as being related when in fact there is no relationship between them. Maybe a more serious example are things like stereotypes. This stereotypes are an oversimplified generalization about a group or class of people. They're often negative. They can be on the surface positive, but oftentimes even positive stereotypes have negative outcomes or effects. So if we're thinking about things like racial or ethnic stereotypes, there's the stereotype that, all Asians are good at math, right? That seems positive, but it's actually very limiting and demeaning to that group of people, right? It's an oversimplified generalization about them. And so, of course, we can have stereotypes about race, ethnicity, gender. You can have stereotypes about geography or location. It's a stereotype that people from big cities are mean, things like that. People very easily make these connections, even though they don't actually have a relationship with one another, or we don't have evidence or data to suggest that there's a relationship between these outcomes. The representativeness heuristic occurs when, and this is also, again, kind of related to something like stereotyping. It's the probability that person A is a member of class B is determined by how well properties of A resemble properties normally associated with B. So that's confusing and difficult to understand. Let's just jump down to this example at the bottom really quickly. So if I asked you, in a group of 100 people, there are 70 lawyers and 30 engineers. What is the chance that if we pick a person at random, they'll be an engineer? I just ask you to answer that question. You should say 30%, because if there's 100 people, 70 are lawyers, 30 are engineers. The probability of picking an engineer is clearly 30%. And people do just fine on this. However, when you add this second part, people start messing it up. So if you said in a group of 100 people, there are 70 lawyers and 70 lawyers and 30 engineers. Jack is a 45-year-old man. He's married and has 4 children. He's generally conservative, careful, and ambitious. He shows no political or social interest and spends most of his free time on hobbies, including carpentry, sailing, and math puzzles. What are the chances that Jack is a lawyer or an engineer, right? Or do you think Jack is more likely to be a lawyer or an engineer? And you start to get a lot of people who say that, well, it's Jack is more likely to be an engineer, when clearly that's not the case. They were just told that there's only a 30% chance that this person chosen at random is an engineer and a 70% chance that he's a lawyer. So why do people make this illusory claim? It's because Jack fits our stereotype about engineers. He's conservative, careful, ambitious. He likes carpentry, sailing, math puzzles, right? It sounds like Jack should be an engineer because it fits this preconceived notion we have about the properties normally associated with being an engineer. Even though, if we just looked at the numbers, it's clearly obvious that Jack is more likely to be a lawyer. And so this occurs when people ignore the base rate information, which is the sort of data, and instead use descriptive information and disregard the base rate. The conjunction rule is similar as well. The conjunction rule is the probability of conjunctive or conjunction between two events cannot be higher than the probability of the single constituents. Again, what the hell does that mean? So if this circle represents all bank tellers, then some smaller proportion of those bank tellers we could probably describe as feminist, right? A certain percentage of people in the world would describe themselves as feminist. Some of them are bank tellers, right? So if we have 100 bank tellers, then, who knows, 25% of them will describe themselves as feminists. And so they would have two category memberships, feminist, bank tellers. And so if you ask people a question like, Cynthia is 30 years old and has a degree in women's studies and is highly involved in local politics and social issues. She attends protests and thinks all of these sorts of things. What's more likely, that is she a bank teller or a feminist bank teller? People will respond feminist bank teller, even though clearly that cannot be the case. It must be more likely that she's a bank teller because bank teller is a larger category that contains the smaller subset of feminist bank tellers. And so even though Cynthia fits our stereotypical description of a feminist, people tend to ignore the sort of categorical nature of this relationship, such that if Cynthia is a bank teller, then it must be more likely that she's just a bank teller than she's a feminist bank teller. People allow those descriptive elements to cause them to ignore this very basic fact of probability. There are obviously more than this, and we're not even listing all of the heuristics that people use here. But here, we're just going to briefly mention a few more. The law of large numbers is the idea that the larger number of individuals that we randomly draw from a population, the more representative the resulting group will be of the entire population. That's true, right? That's a good thing to consider. In fact, when we do science, we want the most representative sample of people. And so we want to sort of look for that representative group. But it depends upon how you drew that group, right? Just because you have a lot of them doesn't make it more representative. It makes it more likely that they will be representative, but it doesn't. Does not necessitate that the larger group is more representative than the smaller group. We want them to be representative, especially when we do science. But just because we have a lot of people doesn't automatically make them more representative. The my side bias is the tendency for people to generate and or evaluate evidence in ways that are biased towards their preconceived opinions and attitudes. So really quickly, I'm going to jump to the next slide here. This is extremely commonplace in politics, even way back in the late 70s, early 80s, although it seems to be more so now. But even if we take something very simple like capital punishment, the death penalty, and we ask people to read an article about the death penalty, people who were politically in favor of the death penalty found the article convincing. People who were against the death penalty found the article unconvincing. Basically, people brought their own bias to the table and used their bias to inform their interpretation of the article rather than letting the article speak for itself and then having a sort of legitimate discussion or interrogation of the article. And lastly, we have confirmation bias, which is the tendency to selectively look for information that conforms to your own hypotheses and overlook information that argues against it. This is the classic Facebook bubble. So if you are conservative, what does social media do for you, right? Based on your behavior, your searches, the things you read and click on, social media and the internet starts to put you in a bubble where all you see is information that conforms to your views, to your hypotheses. If you're politically liberal, the same thing happens. The things that start popping up on your feed in your search returns are things that conform to your preconceived notions. And even more so, how many people do you know that, let's say that someone is liberal and they find out that one of their friends is hardcore conservative. How many people do you know who would say, well, screw that person, I'm not going to be friends with them anymore, right? I disagree with them on politics, so they can go screw themselves. That's essentially creating your own confirmation bias because you're creating your own bubble such that the only people around you are people that conform and agree with you. And both sides in the U.S., we have two main political parties. It's not the case elsewhere. Most other countries have a multi-party system. But so it's easier to talk about in the U.S. It's very easy that if you find yourself on one side of the aisle in the United States, that you sort of cast off and ignore people on the other side. And so you are insulating yourself into your own little confirmatory bubble. Okay, so that's inductive reasoning and then things that can go wrong with inductive reasoning. Next up is deductive reasoning, which is, in a sense, the opposite of inductive reasoning. Deductive reasoning is where we determine whether a conclusion logically follows from its premises. We're going to start with broad information and draw specific conclusions. So it's the flip of induction. In induction, we start with specifics and we move to broad conclusions. In deduction, we start with broad information and we move to specifics. We typically form deductive reasoning statements into syllogisms. Syllogisms include two premises followed by a third statement that we call the conclusion. And we're going to see an example here on the next slide of a categorical syllogism. So the relationship between two categories using words like all, no, or some. So for example, premise one, all birds are animals, right? All A's are members of the group B. So all birds are animals, right? Premise 2, all animals eat food. All bees do C. Therefore, all birds eat food. Right? All A are engage in C. So if all birds are animals and all animals eat food, then it follows that all birds eat food. That's a syllogism. That's deductive reasoning. We have two general statements about birds, animals, and food. And then we draw a more specific conclusion from those two broad statements. Therefore, all birds eat food. So a syllogism is valid if its conclusion follows logically from the two premises. However, the validity of a syllogism should not be confused with it being quote unquote true, or the capital T truth. For example, here we have syllogism number 2. This is going to be a valid syllogism that is incorrect. So, all birds are animals. All animals have 4 legs. Therefore, all birds have 4 legs. This is just not true, right? And the thing that's not true, where we start to get screwed up, is this second premise that all animals have 4 legs. That's not the case, right? There are lots of different types of animals that have different numbers of legs than 4. And so, while this conclusion that thus birds have 4 legs follows validly from the syllogisms, it's not the actual truth. So we can make a distinction here, and this is why deductive reasoning is kind of a little confusing. We have to make a distinction here between proper reasoning, right? The valid process of drawing this conclusion, which this conclusion is valid, but it's not true because premise number 2 is untrue. So deductive reasoning does not necessarily lead us closer to the truth as inductive reasoning necessarily does. People make errors, you would not be surprised, all the time in the way that they judge these syllogisms. So, for example, there's something called the belief bias, which is the tendency to think that a syllogism is valid if its conclusions are believable. So, all of the students are tired. All students, A, are tired, B. Some tired people are irritable. Notice how this is some tired people, C, are irritable, D. So we have not transferred, in a sense, B to C, right? We have started a second premise that has actually nothing to do with the first premise. All students are tired. Great. Some tired people are irritable. Great. That has nothing to do with the students, right? Premise number 2 has nothing to do with the students. But people will accept this conclusion as valid because it seems like it should be. So some of the students, therefore, are irritable. This does not follow from these two premises. The connection between tiredness and irritability has nothing to do logically with the students. So this conclusion, from going from A to D, is not valid, but many people will claim that it is valid. And one of the problems here is the difficulty in creating what's known as a mental model. A mental model is that we can represent these specific situations in our minds, and that we use them to help determine the validity of syllogisms in deductive reasoning. So we basically create like a mock situation in our minds. We then probe and test out some tentative conclusions about that situation, and then we look for attempts to falsify the model, and that we can use that falsification to determine the validity of the syllogism. So, for example, let's do that here with our tired students. All of the students are tired. Right? Every student is tired. So let's say we have a room full of 50 students. We close and we lock the door. Those 50 students are tired and they stay in that room. Some tired people are irritable. We have now made a large statement about some tired people. Well, some tired people are irritable. That could have something to do with our students, but it does not necessarily have anything to do with our students, because our 50 students are not the only tired people that exist in the world, right? There's, let's say, 1 million tired people outside somewhere. And sure, some of those 1 million tired people who are outside are going to be irritable. But just because some of those million people are irritable does not necessitate that anyone in our locked room of students is also irritable. It would be perfectly reasonable for all of our students to, yes, be tired, but the second statement about some tired people does not necessitate that any of our students be irritable. And so the conclusion, some of the students are irritable, is invalid. It's not valid because we don't know that from our previous statements, from our premises. Our premises do not necessarily lead us to this conclusion. And so by constructing literally this sort of visualized mental model of the world, I take my tired students and I put them in a room. I then imagine a world full of some tired people who are irritable. This process is the creation of a mental module. And the idea is we investigate exceptions to this reasoning to try and falsify the model. So this is often expressed in what's known as a conditional syllogism, and we're going to spend some time with this here. A conditional syllogism is an if P, then Q statement. So if I study, then I will get a good grade on the exam. And this has been a very highly studied area of deductive reasoning, these if P, then Q statements, because they actually make up a lot of, in particular, our social functioning in the world. So, for example, if I order a coffee, then I must pay for it. If I text my friend, then they should text me back. These if then statements govern much of our behavior in the world. And so, understanding how people reason about them is actually pretty important. What we find is that sometimes people are good at valid reasoning about these statements, and other times people are poor at reasoning about these statements. So we can take this situation, if P then Q, and we can tell people, okay, if P is the case, right? So the reality of the world is that P is the case. The conclusion is, therefore, Q should be the case. Is that valid? Yes, that one's easy. People get that correct. So if P, 97% of people will correctly judge this syllogism as valid. If I study, if P, then I'll get a good grade, right? Then Q. So I studied P, right? P is the case. P is the truth of the world. If I study, then I'll get a good grade. I studied, therefore, I should get a good grade, right? Therefore, I will get a good grade. That conclusion is valid. And 97% of people will correctly judge it as valid. However, when we start probing and playing with this type of syllogism, performance goes down. So let's look at a second example, which is the no Q example. If I study, I'll get a good grade. That's our conditional syllogism. If I study, I will get a good grade. I didn't get a good grade. That happened. I didn't get a good grade. So is the conclusion, therefore I didn't study, is that a valid conclusion? It is a valid conclusion. So if we're given the statement, if I study, then I'll get a good grade, and then as it turns out, you did not get a good grade, it means that you did not study. That's true. That is a valid conclusion from the conditional syllogism. But only 60% of people judge it correctly as being valid. Performance goes way down. Number 3, if I study, I'll get a good grade. I got a good grade. Therefore, I studied. So this is the Q situation. If P, then Q. So Q happened. I got a good grade. Therefore, I studied is not valid. You can get a good grade without studying. That doesn't violate the conditional syllogism. And it's difficult to see that because only 40% of people correctly judge this conclusion as being invalid. This is not a valid conclusion from these statements. If I study, I'll get a good grade. I got a good grade, therefore I studied. But nothing about this statement says that in order to get a good grade, you must study. That's not what this statement says. I'll say that again. Nothing about this sentence says that if you get a good grade, then you must have studied. That's not what it says. It says if you study, you'll get a good grade. It's perfectly plausible to get a good grade without studying. And so this statement is non-valid. It's incorrect. And people are very bad at this because it's incredibly confusing. Trust me, I know. We will be doing another example with some context to it that shows that this reasoning can actually be made a lot easier in appropriate contexts. And lastly, another difficult, confusing one. If I study, then I'll get a good grade. I didn't study, right? Which is not P. I didn't study. Therefore, I didn't get a good grade. Again, it's the same rationale as the other one. It's perfectly plausible to get a good grade without studying. So this statement is incorrect. It's not valid, but only 40% of people will correctly judge this as not valid. Okay, let's make that maybe in a couple steps a little bit more clear. A very famous set of experiments on this type of reasoning is called the Wason card selection task. And what this experiment did is it gave people these 4 cards. And it said there's a letter on one side of every card and a number on the other side of every card. I'm going to give you a rule. If there is a vowel on one side, then there must be an even number on the other side. That's the rule. If there is a vowel on one side, then there must be an even number on the other side. Which cards do you have to turn over in order to test the rule? Which cards do you have to turn over in order to test the rule? Press pause, and I want you to think about it. And then press play and come back to the experiment, or come back to the lecture, and we'll talk about the experiment. Okay, so if there's a vowel on one side, there must be an even number on the other side. Which cards do we have to flip over? Well, it's obvious that we have to flip over E because there's a vowel on this side. So we need to flip it over and check to make sure that there's an even number on the other side, right? We have to validate the rule by flipping over E. What's less obvious is that we have to also flip over 7. That's difficult to see because 7 is an odd number. And so we have to flip over 7 to make sure that there's not a vowel on the other side. Because if there's a vowel on the other side of 7, then this card violates the rule. So we need to flip it in order to check for that violation. This is, again, very, very difficult. To check for these falsifications, we have to turn over E and we have to turn over 7. When you do this in an experiment, only about 4% of people get it correct. Everybody picks E. E's the easy one. What people have a tough time seeing is that we also have to check 7 in order to check the rule. Notice that this is just a conditional syllogism. If P, then Q. If there's a vowel on one side, then there must be an even number on the other side. But I want to put it into a social context for you. And it's going to show that context matters for conditional reasoning. So I want you to imagine that you are a police officer, and it's your job to enforce the rule that if a person is drinking beer, they must be over 19 years of age. It says here that this experiment is from Florida, where the drinking age was 19 at the time. This was done back in 1982. The drinking age has not always been 21. Okay, so you're a police officer, and the rule is if a person is drinking beer, they must be at least 19 years old. Right? They have to be over 19 years of age. So you walk into a bar, and you see 4 people. You see one person drinking a beer. Obviously, we need to check their age, right? This person needs to get carded. We have to check their age. You see one person drinking soda. We can ignore them. It doesn't matter how old they are because they're not drinking beer, right? So we don't need to check this person's age. We can ignore them. If someone is 16 years old, then we need to flip their card. We need to check and see what they're drinking. But if someone is 24, it doesn't matter what they're drinking because they're allowed to drink beer if they want. So we don't have to do anything to that person. So this is the same task as this. If there's a vowel on one side, then there should be an even number. Then there will be an even number on the other. If someone is drinking beer, then they must be 19 years of age at least. It's the same task, but this context makes it so much more obvious who you have to check. You have to check the person drinking beer, and you have to check what the 16-year-old is drinking. It's clear as day. So what gives, right? From a cognitive psychology perspective, these tasks are exactly the same. Exactly the same. They are both checking for violations of conditional syllogisms. There should be no difference in performance. But people are terrible, like I said, in the abstract version of the task. But when we give them this beer version, this social context, performance goes way up. People are much better at correctly identifying the two situations that must be checked. So what this suggests is that people are using, instead of a falsification schema, they're using what's known as a permission schema, where if A is satisfied, then B can be carried out. And this permission schema is much more concrete, and it's much closer to these sort of social and societal rules that we deal with in everyday life. And that makes it much easier for us to reason about these conditional syllogisms. Okay, we're going to shift gears now and look at decision making, specifically how people are not rational in many of the ways they make decisions. So there's a theory about how people make decisions called expected utility theory. And this theory states that people should be rational. People, if they have all the relevant information at hand, that they will make a decision that results in the maximum payout, the maximum utility. So this is the assumption that people are rational. And what we find is that people's behavior does not adhere to expected utility. People find value in other things. Many of people's decisions does not maximize the probability of their best outcome. People use things like emotion instead of sort of pure maybe mathematics or economic theory in the way that they approach decisions to be made. So a famous example of this is the red bean experiment. Some psychologists said, okay, I have two bowls. In the first bowl, there are 10 jelly beans, and one of the jelly beans is red. In the second bowl, there are 100 jelly beans, but 7 of them are red. You can choose one of the bowls, and if you pick out a red jelly bean, you win a prize, right? You get $10. Which bowl do you want to pick out of? Expected utility theory would say that everyone should pick the first bowl because 10% of the beans in the first bowl are red. You have the best chance of picking a red bean if you pick out of this bowl. But what actually happens is a substantial number of people choose to pick out of the second bowl, even though the second bowl has only 7% red beans. So their odds are worse. People report choosing to pick out of the second bowl because it has more red beans. It has 7 red beans as opposed to the 1 red bean in the first bowl. And so this larger quantity of red beans, 7, makes them feel like there's a better chance, even though there's only a 7% chance in the bowl with 100 beans, and there's a 10% chance in the bowl with only 10 beans. So people are clearly not using math or probability to make this decision. This is a famous occurrence in game shows. And in fact, game shows are actually developed and made in such a way where they often prey upon people's incorrect decisions or the tendency for people to not behave rationally. So a really good example is Deal or No Deal. In this TV show, there are you bring a random person up, and they choose a briefcase from an array of briefcases. I think there's 25 or 30 briefcases or something. And each briefcase has a dollar amount. And so they choose a briefcase. They don't know how much money's in their briefcase. And then they start eliminating briefcases that are still up on the board. And then the show says, okay, you can keep your briefcase or we'll offer you, X number of dollars to just walk away. And so they just continue eliminating briefcases until they either eliminate them all and they're left with their briefcase, or they take the deal, right? That's why it's called Deal or No Deal. So here's an actual example from the game show. A person got down to 5 briefcases remaining. That means they had their one briefcase, and then there were 4 briefcases left up on stage. So 5 briefcases remaining. They had already eliminated all of these values on the left. Those briefcases had already been picked. So these values are no longer in play. But the values left in play were $100, $400, $1,000, $50,000, or $300,000. Which that means is that this person has one of these briefcases. So in their briefcase, they can walk away with 100, 400, 1,000, 50,000, or 300,000. Obviously, they're hoping that their briefcase is the 300,000. So the show offered them $80,000 to walk away. $80,000 to walk away. So let's think about that $80,000. $80,000 is more money than 4 of the 5 remaining briefcases. So there's only a 1 in 5 chance that the person will do better than $80,000. Yet they turned it down. This is clearly not in their best interest. It is in their best interest to take the money and run. Take the 80 grand. It could change your life. Walk away, because odds are you have less than 80 grand, right? There's a 4 in 5 chance that your briefcase is less money than $80,000. But people don't think rationally. People see this 300,000 and they go, I'm going to hope, right? I'm going to keep playing. I'm going to hope that that one is my briefcase. Let me go one more time. Let me go one more time. And they end up screwing it up. And in fact, this person did exactly that. They kept playing. They eliminated the $300,000 briefcase and ended up settling for something like $20,000 or $25,000. So what this tells us is that people do not behave rationally. People allow their emotions to affect their decisions. And in fact, there are a couple rules that we can derive about emotionality and decision making. People are more likely to reject the offer in Deal or No Deal if things are going badly. So for this person, things are going poorly. They're not doing well. They have 5 briefcases left, and 4 of those briefcases have relatively small amounts of money. And some people actually studied Deal or No Deal, and they found that when things are going poorly, people reject the offer. The idea being that they're trying to avoid the negativity of losing. They want to things are going badly, so I want to try again to see if I can make it be better. And what this study found is that when things are going well, people tend to take the offer, right? So imagine if you eliminated all of these low numbers, then the bank, the show, is going to offer you what looks like a pretty good deal, and people take it because they think, I've done well so far, let me walk away before things start going badly. So people try to, if they have an opportunity for a win, for positivity, they take it, and they try to avoid the feeling of negativity by continuing to play, even though continuing to play might not be the rational choice. And in fact, people are even pretty bad at predicting their own emotions about outcomes. This is often a factor in incidental emotions, which are emotions that are not specifically related to making this decision. And those incidental emotions, excuse me, can unfortunately impact people's decision-making processes, even when those emotions are irrelevant. So, for example, people were asked, in this experiment, people were given $5, and they were told, okay, you're going to flip a coin, and if it lands on heads, you get to keep the $5. That's blue. If it lands on tails, I'm going to take $3 from you and you'll leave with $2. And they were asked, predict your emotions before the coin flip about either of those outcomes. How do you think you would feel if you won the coin flip or if you lost the coin flip? People thought that, yeah, they'd be pretty happy if they won the $5. And people predicted their emotions to be very negative if they lost the coin flip and lost 3. Even though it's a net gain, you still walk away with $2. So people predicted their emotions to be very extreme. And then after they actually flipped the coin and then rated their emotions after the coin flip, their emotions were much more subdued. The people that lost, turns out it wasn't that bad. It wasn't that negative. They thought it was going to be really negative, but it wasn't. And even the people that won, they thought it was going to feel awesome, but it was only $5. So it feels good, but it doesn't feel amazing. So people were inaccurate in predicting their own emotions, incidental emotions about the task. Another factor in how we make decisions is that the manner in which choices are presented can impact the decision we make. So a famous example of this is organ donation. So sorry, I'll sort of take a step back. There's sort of two ways that we can conceptualize a decision to be made in this case. Either an opt-in procedure, which would be that everyone by default is not an organ donor. And if you want to be an organ donor, you have to actively opt into it. Versus an opt-out procedure, which is that everyone, everyone is by default an organ donor. And if you don't want to be, then you have to make a decision and opt out. And so what ends up happening is that if you make organ donation an opt-in procedure, fewer people will become organ donors. But if you make organ donation an opt-out procedure, where people are by default organ donors, then there will be more organ donors, even though the decision is the same, right? People have the decision, the agency to either be an organ donor or not be an organ donor. From a utility perspective, there is zero difference between these two situations. You either get to choose to be or not to be an organ donor. What does it matter whether you have to choose to be or choose not to be, right? It's the same thing, but psychologically it's not. There are similar debates about voter registration, right? That's sort of a big issue. Because currently in the United States, in the majority of places, registering to vote is an opt-in procedure. People are by default not registered to vote, and in order to vote, you have to go through a process to opt in. So some places want to make it an opt-out procedure where everyone is automatically registered to vote, and if you don't want to vote, then just don't go vote, right? Opt out of voting. And they're using this research in the hopes that by making voter registration an opt-out procedure, that they will actually increase the total number of people who exercise their right to vote. So this is due to what's known as the status quo bias, which is basically a tendency that people often have, that when faced with a decision, they'll make the choice that requires them to do nothing, right? So this is the kind of the people are lazy bias. When faced with a decision, people often choose the alternative that requires them to do nothing. I'll just keep things the way they are. I'll stick with the status quo. There's also something called the framing effect, particularly in terms of whether we frame a situation in terms of its gains or we frame a situation in terms of its losses. Very famous experiment by Tversky and Kahneman. Daniel Kahneman is actually an incredibly famous um, uh, behavioral economist and psychologist. He won the Nobel Prize for behavioral economics. And they did a series of experiments showing that if a situation is framed in terms of what you can gain from it, then people are very risk averse. They choose the sure thing. Right? They choose less risk in their decision making. Whereas if a situation is framed in terms of losses, people tend to be more risk taking. So they take more risks. So let's make that real with an example. Um, so people were basically told, you're a public health official, and we have some disaster that we need you to make a decision about. And you're the one that has to make the decision about how the city will handle this disaster. You can choose program A, or you can choose program B. In program A, 200 people will live and 400 people will die, and that's a sure thing. We know that that's what's going to happen. We know that 200 people will live and 400 people will die. Or you can choose program B, where there's a 2/3 chance that everyone will live, no one will die. I'm sorry, I said that wrong. There's a 2/3 chance that everyone will die, and a 1/3 chance that everyone will live, everyone will be saved. So we can frame these two choices as the sure thing, the risk averse choice, or program B, the risky choice. Like, you might save everyone, but you might save no one. So choice B, program B, is risky. Program A is not risky. If you frame this to people in terms of what they have to gain, so if you say that you can have a sure chance of saving 200 people or a 1/3 chance of saving everyone, people tend to choose the risk averse strategy, right? So we framed this in terms of the people you can save. 72% of people choose the risk averse strategy. Versus if we frame it in terms of people who will die, so this program will cause 400 people to die, and this program gives you a two-thirds chance of everyone dying. If we frame it in terms of what you have to lose, then people choose the risky option 78% of the time. The point I want to make about this is that these two situations are exactly the same, right? It's either 200 people live and 400 die, 200 people live, 400 die, 1/3 chance that you save everyone, or a 1/3 chance that no one dies, right? These are identical scenarios, but by framing it as saving people versus killing people, it changes people's behavior. It changes the decision that they will make, such that when you frame it as saving people, participants tend to be risk averse, they tend to be conservative. When you frame it in terms of people dying, people tend to be risk takers. They choose the risky option. So, of course, there is neurophysiology that goes along with all of this decision making. Decisions tend to be made globally in the brain, but there are specific areas of the brain that are associated with these emotional decisions. And we actually see emotional activity in those emotional areas of the brain during decision making when people are making emotional decisions versus decisions based on utility. And in fact, people sometimes explicitly use these emotions and express them when making decisions. In particular, there was an experiment called the ultimatum game. And I'll sort of set up the experiment for you. You're sitting at a computer, and you're told that there's another person in the next room, and they're also sitting at a computer. And that person, the other person, has been given $10. And it's their choice about how much of that money to share with you. They can give you all $10. They could give you 9. They could give you 5. They could give you 0. It's their choice. It's their ultimatum. And so on your computer screen, they're going to send you their choice about how much money they want to give you. And then you have the choice to either accept or reject their offer. If you reject their offer, you get nothing. If you accept their offer, then you get whatever they have offered you. So let's think about this ultimatum situation in terms of utility. You, the participant, have a single choice. Do I accept the offer that's been given to me, or do I reject the offer that's been given to me? From the perspective of utility, you should always, always, always accept the offer, because you started with nothing, right? The other person has the $10. You have $0. If they offer you anything, then you're better off than you were before. So an offer of $1 should be accepted every time, because you have no dollars, right? $1 is better than no dollars. So shut up and accept the offer, right? But that's not how people behave. People let their emotions take control. And so what happens is that as the ratio starts to change, people's behavior changes. And people's behavior also changes based upon whether they're told the other person in the other room is actually a human. That's the orange bar. Or whether the person in the other room isn't a person at all. It's actually a computer program that's making the decision. So if the participant is offered a 50-50 split, so if they're offered 5 of the $10, they accept 100% of the time, whether it was a human or a computer. Right? Yep, 50-50, that's fair. So they accept all the time. If they're offered a 7-3 split, where the other person is going to keep 7 and you, the participant, are going to get $3, people accept that at a very high rate, right? $3, yeah, that's fair, I guess. You have 10, you're going to give me 3, that's not bad. So people accept the offer, and they accept it equally whether that person is a person or whether they're told that's a computer. When the offers start to get low, when the participant is offered $2 or $1, something funny happens. They start rejecting the offers, even though they shouldn't. They have no business rejecting the offers. They should only accept offers. But they start rejecting the offers because they get pissed, because they say it's unfair. That person has 10. Why can't they give me more? Why am I only getting $2 or $1? And they especially reject it when they're told that other person is a human, right? Screw that guy, right? I don't need his offer of $2. I don't need his offer of $1. And so a large proportion of people start rejecting. Now, if they're told it's a computer, they reject less, right? They accept more because they're less emotional, right? They're told, in fact, they tell the experimenters, well, it's a computer. I can't get mad at the computer, right? It's just keeping more of the money for itself. That's what a computer should do. But they get mad if they're told it's a human. They get mad at that person. They think that they're cheating. They think that it's unfair. And in fact, when people are making these decisions based on whether they think it's fair or unfair, we see differential activity in particular the anterior insula. That's this section of the graph right here, that when there's more activation of the interior insula, people become more likely to reject the offer. The anterior insula is connected with emotional states. In this case, probably things like anger. And so this emotional arousal, this emotional activity, is actually causing people to reject the offers. And so after decades and decades of this work, Daniel Kahneman proposed a two-system theory of decision making, called it the dual systems approach to thinking, where we have one system that's fast, automatic, intuitive, non-conscious. We're not thinking explicitly about it. And that's generally where we operate day to day. We let this quick automatic decision-making mechanism take over most of the time. However, we have a second system that's more slow, deliberate, conscious, and controlled. And we allow this system to take over. We use this system when we need to make a more difficult or a more thoughtful decision in the world. And so system one might be said to be more emotionally based. And that's why you get people maybe making these rash decisions in the lab and getting angry. And system two can be thought of as being more about the utility, expected utility theory here, where, whoa, let me take a step back. Let me really think about this and make a rational, conscious decision. And so decision making can be thought of as this sort of back and forth between these two systems. All right, that's it for chapter 13 on judgment, reasoning, and decision making. Thanks, everybody, and I will talk to you next time.